In previous lessons, we've learned how to solve quadratic equations by a couple of methods with which you're familiar. The first is by factoring a trinomial when it's set equal to 0, and then using the zero product property to generate the two values of x that are solutions to the equation. We've also taken the square root of both sides. Now we can combine taking the square root of both sides with what you guys know about perfect square trinomials to generate another way to be able to solve quadratic equations. And this is a method called completing the square. We're going to take a look at just these two terms, x squared minus 6x, and think about what would we need to add on to this expression to create a perfect square trinomial. And as we took a look at this in class, several of my students, if I said, hey look, if we go x squared minus 6x and I want you to add a number here that would make that a perfect square trinomial, were able to tell me 9. If I said y, several students said, well, it's a perfect square. I know I multiplied two numbers times themselves and got this 9, and those two numbers had to add up to 6. And they recognized that that would be 3 and 3. In particular, x minus 3 times x minus 3. And we could write that in the form of a binomial squared, x minus 3, the quantity squared. So they were able to come up with that by brute force. But what if we could generate a way that's more efficient, that would tell us what that value would be every single time? And if we think about how we come about those perfect square trinomials, let's work backwards. I'm looking at this number 6. We took half of that number, in fact negative 6. Divided it by 2, that gives us negative 3. If we took that negative 3 and squared it, that gave us 9. Make that an equal sign. And that's where this number came from. So we're using this expression, b over 2, that quotient squared. If I take the b value, divide it by 2, and then square that result, that will give me this value. Here's another one you can try on your own. What's the value of c that makes x squared minus 12x plus c a perfect square trinomial? Once you come up with that, go ahead and write the expression as the square of a binomial. If you'd like to stop the video now and give that a try, do that. Using our formula, b over 2, that quotient squared, our b value is negative 12. Negative 12 divided by 2 is negative 6. If we square that, we get 36. We'll need to write x squared minus 12x plus 36, which can be written as x minus 6, the quantity squared. Alright, so this is a lot of fun, and I'm sure a great trick at parties, but so what? Why would we ever want to do this? So in class, I challenged my students to factor this expression, x squared plus 8x plus 3. And in particular, to think about it as a quadratic equation, x squared plus 8x plus 3 equals 0. And let's solve that by factoring. And after struggling for a couple of minutes, eventually, they'd say, you can't do it. Well, what do you mean you can't do it? They said, look, I would need two numbers that multiply together to make 3 that add up to 8 in order to be able to factor this. And we pointed out that those two numbers don't exist. I said, well, does that mean that there are no solutions? The students thought about that for a minute, and I challenged them to take out their phones and to open up their Desmos app. And we graphed that function. So x squared plus 8x plus 3. And when we did that, we noted that there were, in fact, two places where this graph crossed the x-axis, at negative 0.394 and at negative 7.606. We talked about the relationship between the graph of a quadratic function and the solutions of the related quadratic equation, that the x-intercepts of the function were in fact the solutions to the equation. So we know that this equation has solutions. The question is, how are we going to get to them? So this is where completing the square comes in. we can use this method to create a perfect square trinomial on the left-hand side. Rewrite that as the square of a binomial, and then take the square root of both sides. And when we do that, we'll have our two solutions. So the first thing I want is my x squared plus 8x alone on one side of the equal sign. So let's subtract 3 from both sides. X squared plus 8x equals negative 3. My next question is, what do I need to add here and here to create a perfect square trinomial on the left-hand side? B over 2, that quotient squared. So 8 over 2 is 4. Square it, I get 16. So if I add 16 on the left-hand side, x squared plus 8x plus 16, I've got a perfect square trinomial, which is great. But remember, if I add 16 on the left side, I need to add 16 on the right side also. Let's simplify. I know this is a perfect square trinomial because I picked the 16 on purpose to make that happen. X squared is x to the second power. 16 is 4 to the second power. This is positive. X plus 4, quantity squared, equals 13. Okay, now I can take the square root of both sides, and I'm going to move back up a little bit farther on my page so we can see what we're doing here. So when I take the square root of both sides, taking the square root of something squared, those two operations undo each other, and I have just x plus 4. On the right-hand side, plus and minus the square root of 13. Every real number has a positive root and a negative root. So now, let's continue solving for x. Subtracting 4 on this side, just x. On the left-hand side, this is going to look pretty strange. Negative 4 plus or minus square root of 13. It's not the way we talk. It's a really unusual number, but it also happens to be the exact value of the solutions. If you go ahead and you box up that answer, that is absolutely 100% correct. But just to reiterate that point, in class, again, we went back to Desmos. Took a look at those two solutions. Negative 0.394, negative 7.606. And I challenge my students to go ahead and take out their calculators and punch in negative 4 plus square root of 13, negative 4 minus square root of 13, and they saw it, they matched up with those approximate decimal values. They could see that this is the solution to that quadratic. One more thing that we can use completing the square for is to rewrite a standard form equation in vertex form. Remember, vertex form will give us the coordinates of the vertex, which sometimes can be useful for us, especially if we're solving word problems. So the way that we're going to do this is, I want an equation that's written in y equals x minus h, quantity squared, plus k. And then the vertex is the ordered pair h comma k. Well, how can we make that happen? I'm taking a look at x squared minus 10x. Let's see if we can rewrite one side of this equation as a perfect square trinomial. I'm looking at the 10, negative 10 in fact. Half of negative 10 is negative 5. Negative 5 squared is 25. I need to add 25 on both sides. So y plus 25 equals x squared minus 10x plus 25 plus 22. This portion here now is a perfect square trinomial. So x squared minus 10x plus 25 we can rewrite as x minus 5 quantity squared. So now I've got y plus 25 equals x minus 5 quantity squared plus 22. Now we just need to get y by itself on this side. I'm going to subtract 25 from both sides. and I get y equals x minus 5 quantity squared minus 3. That's the equation in vertex form. The vertex itself, my h value is 5, the k value negative 3. Quickly, let's practice a couple. Practice number 1, x squared plus 6x equals negative 3. I can see that half of my b value is 3. 3 squared is 9. X squared plus 6x plus 9 equals negative 3 plus 9. The left-hand side, this is a perfect square trinomial. Let's write it as the square of a